All right, so this is a little guided instruction for States of Matter Lesson 5 in this textbook that you got yesterday. And we will be on page 64. So just to give you a little bit of a visual of what we're doing here, we'll be on page 64. So let me kind of make sure we're zoomed out as much as we can. All right, I'm going to try to adjust this camera and see if I can get it to zoom out even more. There we go. That's a little better. All right. So on page 64, as you can see, it is lesson 5, and it is called States of Matter. How do particles in solids, liquids, and gases move? So we've been talking about that. We've done a few investigations. We've done a lab simulation where we saw particles in liquids move. So this is just going to give us some more information along with some vocabulary. All right, page 65, this is an engage your brain. Hey, look, changing volumes in a can crusher. So we did do that lab. So it does kind of all relate. Okay, engage your brain. This page is not a page that you really need to spend a ton of time on. It just kind of gets our brain thinking about the topic. So number 1 says, fill in the blank with a word or a phrase that you think correctly completes the following sentences. So you just have to give an example of a solid. So it can be any solid that you can think of, okay? And then what would be an example of a gas? So think about what might we have around us that we really can't see, but we know it's there. So what is an example of a gas? And unlike solids, gases can blank. So I know that the pen that I'm holding here is a solid. Okay, so that would be a good example of a solid. And I know that this pen can't really move around a whole lot unless I force it to move. So I can pick it up and move it, but on its own, it can't really do much movement. Okay, but can gases? So think about gases. Can gases move freely? Well, if you think about wind and blowing. You know, we're blowing through our mouths, we blow, and so we can force air to move. So unlike solids, gases can move freely. All right, number 2, unscramble the letters below to find substances that are liquids. Write your words on the blank lines. So these are liquids. So what liquids could these be? Seems to be the hardest for most students. I'll give you a clue. It starts with a V. The others I think you can figure out. And this one's hard too. It starts with an S. Something that you might use in the morning or in the evening would be that one there. All right, and number 3, use context clues to write your own definitions for the words definite and occupy. So the example sentence says solid is the state of matter that has a definite shape and a volume. So based on that sentence, what does definite mean? Well, we can say that something that has a definite shape and definite volume means that maybe its shape doesn't change, its volume doesn't change. So definite can mean not changing, always the same, with boundaries. Those could be some definitions for definite. How about this one? A large container will allow a gas to occupy more space. So if I have a large container, the gas will occupy more space in a large container as opposed to a small container. So what is the word occupy? Think about how you can replace that word with another word and the sentence still makes sense. A larger container will allow a gas to take up more space. Could be something we could replace the word occupy with. So occupy means to take up. Okay? Would be a good definition for that. We do not need to do the vocabulary terms, but it does say as you read, place a question mark next to any words that you don't understand. And when you finish reading the lesson, you can go back and review the text that you marked. If the information is still confusing, consult a classmate or a teacher. But we'll be looking at solid, liquid, and gas as our vocabulary. All right, and particles in motion is our first section. So the paragraph says, how do particles move in solids, liquids, and gases? All matter is made of atoms or group of atoms that are in constant motion. This idea is the basis for the kinetic theory of matter. How much the particles move and how often they bump into each other determine the state of matter of the substance. This view of a movie theater helps to illustrate the differences between the particle motion in each of the three common states of matter: solid, liquid, and gas. In solids, particles vibrate in place. So we're talking about how particles move. A solid substance has a definite volume and shape. The particles in a solid are close together. Take a look at the picture. They do not move freely. The particles vibrate but are fixed in place. Often the particles in a solid are packed together to form a regular pattern like the one shown at the right. For most substances, the particles in a solid are closer together than the particles in a liquid. For example, the atoms in solid steel are closer together than the atoms in liquid steel. Water is an important exception to this rule. The molecules that make up ice actually have more space between them than the molecules in liquid water do. How are the particles in a solid like people sitting in a movie theater? Well, look how they're packed close together, much like this picture. They are sitting in rows. They are not randomly spaced. Okay? They are not moving freely. They are just moving in their seat in a fixed position. So particles in a solid are like people sitting in a movie theater in those ways. So we'll write that down. The people are sitting close to each other. They're practically touching in rows. They are not randomly spaced and vibrate in their fixed position. And what I mean by that is they basically just move in their seat and not around. Move in their seats. Okay? Just like solid particles are just vibrating in a fixed position, but they don't move around freely. Now, if you need to pause this video to continue writing and answer number 5, then go ahead and pause the video and then hit play when you're done. Next page. In liquids, particles slide past one another. A liquid substance has a definite volume, but not a definite shape. Particles in a liquid, shown at the right, have more kinetic energy than particles in a solid do. The particles are attracted to one another and are close together. However, particles in a liquid are not fixed in place and can move from one place to another. So here they are shown kind of in a motion. We can see that there are these little motion shades or shadows kind of around our particles to show that they are moving around. How are particles in a liquid like people in a movie theater lobby? Well, what I can see is that they are close together. They are moving around freely. They are not fixed in place. They can go from the concession stand over to the door, or they can move to this area of the lobby. They can go look at the pictures, so they can move around. But they are not very far apart. They are close together. So we're going to say that the people in the lobby are close together, but not attached. in fixed positions. They can move freely. Okay, if you need to pause the video to continue writing and get that done, go ahead and pause it and then you can hit play again. In gases, particles move freely. A gas does not have a definite volume or shape. A substance in the gaseous state has particles with the most kinetic energy of the three states. As you can see in the model at the right, gas particles are not as close to one another and can move easily in any direction. There is much more space between gas particles than there is between particles in a liquid or a solid. The space between gas particles can increase, so the space can get bigger, or it can decrease, so the particles can move closer together, with changes in temperature or pressure. How are particles in a gas like people outside of a movie theater? So we can see that outside of the movie theater, there's a lot more space. People can spread out more. We're not going to have as many people in one area because they're more spread out. So we're going to say the people are not close to each other or to one another. And can move more freely and quickly. All right, again, pause the video to finish writing that, and then hit play, and we'll move on to page 68. Page 68 says, shape up. How does particle motion affect the properties of solids, liquids, and gases? Imagine what you would see if you put a few ice cubes into a pan on a hot stove. The hard blocks of ice would melt to form liquid water. If the pan is hot enough, the water would boil, giving off steam. Ice, liquid water, and the gaseous water and steam are all made of the same water molecules. Yet ice looks and behaves differently than water or steam does. The kinetic theory of matter helps to explain the different properties of solids, liquids, and gases. So what we're going to do in number 8 is we're going to underline words or phrases that describe the properties of solids, liquids, and gases as we read each of these sections. Okay, so we'll start with solids. So again, we're looking for words or phrases that describe the properties of solids. Solids have a definite volume and definite shape. The fishbowl at the right contains a small toy castle. So we can see that right there. When the castle was added to the glass container, the castle kept its original size and shape. The castle, like all solid substances, has a definite shape and volume. So I think that's a characteristic that we can underline. All solid substances has a definite shape and volume. The container does not change these properties of the toy. The particles in a solid are in fixed positions and are close together. Again, that's something that's describing solids. Particles in a solid are in fixed positions and are close together. Although the particles vibrate, there's another one, they cannot move from one part of the solid to another part. As a result, a solid cannot easily change in shape or volume. If you force the particles apart, you can change the shape of a solid by breaking it into pieces. However, each of those pieces will still be a solid and have its own definite shape. We are going to skip number 9. So we're going to go on to liquids and then gases. Again, underlying those characteristics. Liquids have a definite volume but can change shape. Unlike the solid toy castle, the water in this fishbowl does not have a definite shape. The water has taken the shape of the round fishbowl. If you poured the same water into a rectangular fish tank, the water would take the shape of that container. However, the water would have the same volume as it did before. It would still take up the same amount of space. Like water, all liquids have a definite volume but no definite shape. So liquids have, we'll say water. Whoops, that's the wrong one. All liquids have a definite volume but no definite shape. The particles in the liquid are close together, but they are not tightly attached to one another. Instead, particles in a liquid can slide past one another. As a result, liquids can flow. Instead of having a rigid form, the particles in a liquid move and fill the bottom of the container they are in. Gases can change in volume and shape. The small bubbles in this fishbowl are filled with gas. Gases do not have a definite volume or shape. So we'll underline that. The particles in a gas are very far apart compared to particles in a solid or a liquid. The amount of space between particles in a gas can change more easily. If a rigid container has a certain amount of air inside and more air is pumped in, the volume of the gas does not change. The gas will still fill the entire container. Okay? Particles will become closer together. If the container is opened, the particles will spread out and mix with the air in the atmosphere. I do want to underline this right here. So go back, we're going to underline the amount of space between the particles in a gas can change more easily, meaning that they can easily be pushed together and they can easily come apart from one another. Okay? All right, number 10, identify substances A, B, and C as a solid, a liquid, or a gas by placing a letter in each of the small circles below. In the larger circles, draw models of the particles of each substance. All right, so in this fishbowl, you have to decide, are these bubbles solid, liquid, or gas? The castle, is that a solid, liquid, or a gas? And then this water inside the fishbowl, solid, liquid, or gas. So what you're going to do is place the letter. So which one is a solid? Was it A, B, or C? So we're going to place A, B, or C here. Which one is the solid? If you chose B, you were correct. Okay, which one is the liquid? A or C? If you chose C, you were correct. That means our gas, these bubbles, those have gas inside of them. They have air. So that is our A. Now, we want to draw models of particles of each of these substances. We did learn back here that solids look like this, liquids, particles look like this, and gas particles look like that. So we're going to draw solids. You do not have to take up the entire room of the circle, but you do have to show them close together in a fixed position, and they are in rows. They are rigid. Liquid particles are close together, but they're more random. They're not really touching, but they can be. They can touch each other. They kind of glide past around one another. And liquids, spacing is very far apart. We're going to have them filling up the entire container. Okay? If we were being more accurate, maybe our liquid particles would be at the bottom because gravity is going to pull them down, and they're going to be at the bottom of a container, just like if you were to have a glass of water. And if our solid was at the bottom of the container, gravity would pull that whole solid piece down. Like if this were a block or a Lego, it would be at the bottom. But we were just drawing their spacing. All right, page 70. What happens when substances change state? Ice, liquid water, and water vapor are different states of the same substance. As liquid water turns into ice or water vapor, the water molecules themselves do not change. What changes are the motion of the molecules and the amount of space between them. The motion of the particles changes. As particles of a substance, even a solid, are always in motion. As a solid is heated, its particles gain energy and vibrate faster. If the vibrations are fast enough, the particles break loose and slide past one another. This process in which a solid becomes a liquid is known as melting. As the temperature of a liquid is lowered, its particles lose energy. Eventually, the particles move slowly enough for the attractions between them to cause the liquid to become a solid. This process is called freezing. Because water freezes at 0 degrees Celsius or 32 degrees Fahrenheit, you may associate freezing with cold temperatures, but some substances are frozen at room temperature or above. For example, an aluminum can is an example of frozen aluminum. It will not melt until it reaches a temperature above 660 degrees Celsius. The table below shows the most common types of state changes. When substances lose or gain energy, one of two things can happen to the substance. Its temperature can change or its state can change, but both do not happen at the same time. The energy that is added or removed during a change of state is used to break or form the attractions between the particles. If you measure the temperature of boiling water, you will find that the temperature stays at 100 degrees Celsius until all of the liquid has become a gas. So let's come up with an example of something melted, where a solid becomes a liquid. I can think of a chocolate bunny. Put it in the sun, it's going to melt. Something that freezes, a liquid, becomes a solid. I'm going to say heavy whipping cream is a liquid. When it is frozen, it becomes ice cream. Now, some other things might have to happen to get it to become ice cream, but if you were to put heavy whipping cream in the freezer, you would get something similar to ice cream. Boiling, a liquid becomes a gas. Well, we could say water becomes water vapor. Evaporation, a gas becomes a liquid. So I skipped it. Evaporation, a liquid becomes a gas. This would be a puddle drying out. Condensation, a gas becoming a liquid. Clouds. This is what happens when clouds are formed. Sublimation, so there's two others that maybe you haven't heard of yet. This is when a solid becomes a gas. Dry ice. So you might have seen this at maybe a haunted house or in the theater. If you see like fog on the ground, that's dry ice. They take it out of the freezer, and when they put it in a room temperature room, it becomes gas, skipping the liquid stage. Deposition, a gas becoming a solid. Frost, forming on a cold window pane, is when the gas in the air, the water vapor, skips the liquid stage and just becomes frost right on your windshield. We are going to skip page 71, and I'm going to have you can do number 15, 16, and 17 on your own. It says to complete the summary, check the box that indicates true or false. Then use the key below to check your answers. So down below, you have the answers. Do the questions first, do the true and false first, then check your answers, okay? And then the lesson review. So the lesson review is vocabulary. So you have to, number 1, 2, and 3 are vocabulary. Solids, you have to find the definition. Liquids, what definition is it? And gas. Then what is the kinetic theory of matter? You can go back into the section and find the kinetic theory of matter. So the kinetic theory of matter is going to be right at the beginning, and you will find that definition right on page 66. Okay? What happens to the temperature of a substance while it is changing state? You're going to find that on page 70. It's going to be in this paragraph right there on page 70. What could you do to change the volume of a gas? Think about a balloon. If you want the volume, if you want this amount of space that gas takes up, what would you do to a balloon? Number 7, can a tank of oxygen gas ever be half empty? Think about what particles of gas do. Do they spread out? Are they going to take up the entire tank, or can they condense and still be gas and only be half full or half empty? Number 8 and 9, this jar has helium gas. What would happen if the lid of this jar was removed? So what if we took off the lid? What would happen? How are helium atoms in this model different from real helium atoms? And then finally, number 10, particles that make up a rock are constantly in motion. However, a rock doesn't visibly move or vibrate unless you actually moved it yourself. So why do you think that is? Why are the particles constantly in motion, even though the rock is not moving? All right, there you have it.